Jenny and Burley, who may or may not be joining us for this class. I'm not sure. So, any big plans this weekend? Anything happening exciting? Calculus. That is exciting. Work. Work and calculus. Both of those might be too much, but sounds like you'll have to do it anyway. I don't know if I've got any big plans. My mom and dad are here from Washington, so yeah, so it is kind of fun hanging out with them, and yeah, this weekend will be nice. It's hard when I'm working because I can't focus on two things at once sometimes, but it'll be fun this weekend to spend some time with them. So yeah, I hope you enjoy your weekend. Catch up on everything you need to this first week. But let's go ahead and look at this one is the one that we left off on. So this is a definite integral from 1 to 5 of m over e to the m dm. This is actually probably similar to one of your homework problems from last night. One thing that's hard with this is the e to the m is in the denominator. So in this one, you probably want to bring that up first and call it e to the negative m so that you can see what your parts are. Integration by parts isn't meant to use one of the parts in the denominator. You either need to write it as a fraction or bring it up to the numerator like this and call it e to the negative m. Does that make sense? You've done that before, right? You can bring that up and call it a negative exponent. So if you see it in this form, remember integration by parts, we're trying to look for our two parts, u and dv, to start. Which one do you think I would let be u on this one? M or e to the negative m? E to the negative m for u? Okay, then dv would be m dm. Okay, let's try that. So then what's du going to be? Yeah, what's the derivative of the exponential? It stays the same, right? Do I need to do anything with this one? A dm. What else? What else is important about this negative piece? Is that going to affect it at all, or is that okay? Yeah, you should make it negative, right? So this is like the chain rule. The derivative of an exponential, it stays the same, but you're going to multiply by the derivative of the inside. So you'll need to multiply by a negative here. How am I going to find e of v? Remember what we got to do? With this, you got to integrate, right? What's the integral of m? Yeah, 1/2 m squared over 2. Okay, so let's see how this works out. So have you gotten the formula down yet? What is it? uv minus the integral of v du, right? So don't forget that. I just try to memorize the result. It's uv minus the integral of v du. So filling in those pieces, you have e to the negative m times 1/2 m squared minus the integral of, what's the new integral going to be of? It's going to have a negative e to the negative m and the 1/2 m squared, right? So negative 1/2 m squared e to the negative m dm. Are you getting nervous at all? Because I am, because this, like, how am I going to integrate that? Does that even look like something I can integrate? And in fact, it looks more difficult than what I started with, right? So this is an issue. I'm getting here and I'm like, how am I going to integrate this? Especially if I've created something that's even harder than what I started with. So if I get to this and I'm wondering how to integrate this, what should I go back and be doing? Abandon ship is a good option here. What should I fix? The u and the dv, right? So that means I probably didn't choose these correctly. So, and in fact, if I choose this to be m, I usually here get something that's a little more complicated than I integrate. If I choose it to be u, I get an easier du. So we'll abandon ship on this one. Use pencil, or hopefully you used pencil. And go back and fix it. So that's usually what you'll see if you haven't chosen correctly, that you get something you can't really do. So instead, I'm going to make this m and this e to the negative m. Now it should work a little bit better, right? What's du going to be? dm, which I always like. And v, now when you integrate this exponential, what should I get? Yeah, it should stay the same again, right? Its derivative, its integral are the same, but with the negative. This time we'd have to divide by the negative. Up here we multiply by it, but you still get the same thing when you divide by -1. So now if I follow this formula, I get uv. So u times v, that will be m times e to the -m, but with a negative out front. So I'll just pull that negative all the way to the front. So it's m times -e to the -m minus the integral of, now this, right, is -e to the -m, v, and the du is dm. Okay, now is this something I could integrate? Yes, and in fact I integrated it back here, right? So I know how to do that, so I'm on the right track. So let's finish that off. So -m e to the -m. I'm trying to figure out what the final sign is going to be here. These two negatives make a plus, but when I integrate this, I'm going to have to put on another negative, right? So it really will end up being negative. Yeah. Are you back online? Okay. Okay. All right. Josiah, he can't see the notes or anything like that. If you could switch the screen for him. Only me, not that important. The notes are definitely more important. Okay. You're only seeing me. Yeah, he did. I think they're working on it. Hopefully. Thanks. Hi, Jonathan. I'm glad you could join us. And if you missed that first problem, I am recording this, and I'll post it on the website later this afternoon. So if you missed that one, that'll be okay. Oh wait, there wasn't a plus C, was there? I forgot. What should I have done at the end of that one? It had some limits, right? Good thing I looked back. From 1 to 5. So let's finish that one off. Should have noticed that at the beginning. Alright, so once you have your limits, we'll just plug those in, 1 and 5. So let's see, plug in 5 first. So -5 e to the -5 minus e to the -5. There should each be 5s there. Minus -1 e to the -1 minus e to the -1. Is that right? I think so. Can we combine anything here? Yeah, these are like terms, right? How many of the e to the -5s are there? -6 of them. So -6 e to the -5. And these are like terms. There's -2 of them. But these negatives will make it +2. So plus 2e to the -1. There we go. All right. So do you remember kind of a problem similar to this on your homework from last night? Z over 10 to the z. That one should have been kind of done like that. Like you bring up the 10, make it a -z, and then kind of use those as your parts. So that should have been similar to that one. Hopefully you did that one. Yes. So this is hard just remembering how to integrate, right? Like how do I integrate e to the -m or 10 to the -z? So that's the hard pieces sometimes. Let's do one more here before we go to a couple different kinds. This one is x sine of x cosine of x dx. And we're going from 0 to pi. So let's talk about this one. And what we want to choose to be u and dv. Any thoughts on this one? What do you think for u? X, sine of x, cosine of x, or there's really like 3 parts. We're going to have to put a couple of them together, right? What would you probably put together? I'm thinking maybe sine and cosine, right? Maybe. So the easiest thing to differentiate is the x, so maybe I'll choose that here, this to be the simpler part. But if I choose dv to be sine cosine, do you know how to integrate that? We're going to have to integrate sine x cosine x. Or is there an identity we could rewrite it as? Anyone know of anything we could do? So I know du, right? What's du? du is going to be 1 dx, right? How would you integrate sine x cosine x? Could you? Okay. So it wouldn't be too hard with substitution, right? What would you let be the u? One of them, right? Because the other one is its derivative. So it probably wouldn't matter. What if you let it be sine and then du is the cosine? Because you have 1 and here's its derivative. That shouldn't be too hard because then it's just u du. And that becomes u squared over 2. Or just 1/2 the sine squared of x. So yeah, we can integrate this. You might have to do a u substitution like that, right? And so this is our u, all of this is our du. And we just do a power rule u squared over 2, which is just 1/2 that sine squared, or u squared. Is that okay? Probably. Maybe. It'll depend if we can integrate that when we're done. Okay, so let's see if we can. So our formula is uv minus the integral of v du. So filling that in, the u and the v, that would be 1/2 x, right? 1/2 x and then the sine squared of x, minus the integral of, our v now is 1/2 sine squared of x, and du is just a dx. Do we know how to integrate sine squared of x? I know how to do sine, but do we know sine squared? No. Okay, so is there possibly, though, a trig formula that I could use that would make this something I could integrate? You would know a formula for sine squared of x? Anyone know that? 1 minus cosine squared, but then you're still left cosine squared, so that might be a problem. Anyone else? Okay, so what's the identity? You tell us that. That is right. That's exactly right. 1 minus cosine of 2x all over 2. This is called a power reducing formula. You may have seen it in trig, maybe not, but that is exactly right. Sometimes you might see it have written like 1/2 in front of this, 1 minus cosine of 2x. Some people write it like that, so either of those. But this will be much easier to integrate if we use this form. So I get kind of stuck here. Does that mean I did it wrong? Not necessarily. It just means you may need to use some other piece of information, especially with trig functions, a trig identity to help you actually integrate this. So if we replace that, let's see if we can integrate that now. So if I have now 1/2 x sine squared of x minus, now this already has a half out front, so if I put another 1/2, that will make a total of a 1/4, and then the 1 minus cosine of 2x dx. So I'm substituting that in. There is already a half there, so it's going to be a 1/4. Okay, so do I know how to integrate now? Do I know how to integrate 1? Is that going to be okay? That's no problem. Do I know how to integrate cosine of 2x? Yeah, you could just do a u is 2x, right? And then just integrate it regularly like a cosine. And you can actually probably do it without substitution. Technically you might need it, but I'll show you how to do that here. So let's try to integrate this piece. So I'll have a 1/4. What's the integral of 1? That should just be a what? X. Good. What's the integral of cosine usually? Yeah, it's actually just sine. So this cosine integrates to just sine. Now, how do I adjust if there's a 2x inside? You can technically do a u substitution, but when the derivative of the inside is just a constant, all you really need to do is adjust for the constant, right? What do you do with it? You divide by it. Yeah, it's like when you do derivatives, you multiply by the derivative of the inside. When you integrate, it's really you're just dividing by that constant that's on the inside there. That only works if there's just a constant derivative, but that will work there. So that becomes negative 1/2 sine of 2x. And of course, no, we don't want a plus c on the end. We want a 0 to pi. So I'm going to clean it up a little bit, and then I'll plug in the limits. I'm just going to distribute this negative 1/4 through, probably. You could leave it, but I'll write this as negative 1/4 x plus 1/8 of sine of 2x. And then I'll go ahead and plug in those limits 0 to pi. I'm hoping 0 will just make 0, but it looks like I might have some pi's here. So this will be 1/2 pi. What's the sign at pi? If I plug it in here, sine of pi is 0, so luckily that's all 0. Then minus 1/4 pi plus 1/8. What's the sign at 2 pi? Also 0. I like it. And when I plug in 0 here, I'm going to get 0, right? Because 1/2 x is 0 is 0. This is 0. 1/4 times 0 is 0. And the sign at 0 is 0. So all of those should be 0. Are there anything that's not 0 here? Yeah, I think that's it. That was the only thing, the negative pi over 4. Or 1/4 pi, however you want to write it. So that, after all the work, that is my final answer. Okay. So this is kind of an interesting one with trig functions. Just be careful with those. We know how to integrate most of the trig functions, sine and cosine. And so this may look like something you can't integrate, but we can here with the u substitution. Also here, always ask yourself, well, I might not be able to integrate this, but is there some identity I could use to maybe switch it? And we're going to talk more about that. There's a specific section in 7.3 where we talk a lot about trig functions and their identities and how to help us integrate those, but that's another one you can use. This is sometimes called the power reducing formula, and there's one for sine squared, cosine squared, and tangent squared, which is kind of interesting there. Okay, so that's more fun, integration with parts. Questions on that one? So lots to remember. Okay, well, let's look at maybe the new part of this second half is sometimes you may need to use integration by parts more than once to get to your answer. So that's what we're going to see here. So we may have to do it once, and then we get an integral, and we may have to apply it again to the second integral that we get. So we're going to see that possibly happen in a couple of these. So we're still using integration by parts. This one's t squared sine of bt. Now b here just represents some constant, so it could be 5t, 2t, but it's just a constant. So b here is a constant. So let's go ahead and start u and dv to start with. Remember, you want to usually choose to be the more simpler part right here. So what would be your u? T squared. Good choice. Okay. dv, let's make sine of bt, dt. Okay, so if I set it up like that, let me start over here with Taylor. What's our du going to be? What's the derivative of t squared? 2t with a dt. Yep. Good. V, how do we integrate the sine of bt? Natalie, what's the integral of sine? Do you know what that is? Negative cosine. Good. So we're going to get negative cosine of bt, but what are we going to do with the b? Divide it, because it's the constant, right? So when the derivative of the inside is just a constant, you're going to divide that out front. So I'm just going to call it 1 over b cosine of bt. So that's kind of the shortcut now. We're going to see that a lot. That works only if the derivative of the inside is just a constant. You can do that. Okay, so now following the formula, we will need to put in uv minus the integral of v du. Okay, so I'm filling in those parts. So I should have u is t squared, v is times negative 1 over b cosine of bt, is all of v, minus the integral of v which is this negative 1 over b cosine of bt times du. Okay. Times a 2t dt. Okay, so let's see if we can integrate this, right? That's our goal, is to integrate that. I'm going to clean up the front a little bit. I'm going to call this negative t squared over b cosine of bt. This I'm going to make into a plus, the two negatives. And what I really have there is a 1 over b, 2 over b out front, I guess you could call that. 2 is a constant, right? B is a constant. And then we have a t cosine of bt. So it might help you there to kind of just separate what as a constant out. So the 2 is a constant, the b is a constant. I'm just going to put that as a fraction out front. So really what I'm trying to integrate now is a t cosine of bt. Can I integrate t cosine of bt just as it is? No, because it's like t with cosine. But it's kind of similar to what we started with, right? So I can probably just use another integration by parts on this. So now I'm going to try to do integration by parts on just this integral here. So I'm going to set up a new 4 parts off to the right. Now, technically you should maybe change variables, but I just usually make them capitals if you want to differentiate a little bit. So maybe capital U and capital V. We'll just use... Right, you could use W, you could use, you know, anything you want there that we haven't already used. So X and Y, anything. So I tend to always use U's and V's because that's how you memorize the formula, but it wouldn't matter. If I did this again, what would be my U? T, right? We had t squared to start, now let's use t, and now dv will be the cosine, right, of bt. So that shouldn't be too bad, right? So now what is du going to be? Joel, what would it be here? Yeah, the dt. And Angie, what would you get if you integrate cosine of bt? Yeah, sine of bt over b, right? So you got to divide by the b, so 1 over b sine of bt. Very good. Okay, so don't forget, you got to kind of drag this first part along, the negative t squared over b cosine of bt. And don't forget, you also have a 2 over b in front of this whole thing. You could leave it inside and make it part of your u's and v's, but I just put it on the outside, so make sure you don't forget to put that in the front. So remember, we're still following the same formula, uv minus the integral of v du. So that's what I'm going to put in here. So u is t times v is 1 over b sine of bt. So uv minus the integral of v, which is 1 over b sine of bt dt. Yep, so in this brackets is what this integral is equal to using the formula. uv minus the integral of v du. Okay, now I'm close to getting done. Can I integrate this last piece then? Yeah, because what's the integral of sine? Yeah, negative cosine. So that shouldn't be a problem. And 1 over b is now just a constant. So I should be able to finish it right here. So just don't forget to bring everything else along. Okay, negative t squared over b, cosine of bt. You have this 2 over b out front. You could call this t over b sine of bt. Minus, so we already said this was going to be, the integral of sine is a negative cosine, right? So this should change it to a plus. And what will be the fraction out front when I integrate? 1 over b squared. Very good. Cosine of bt. And then I can finally put on my plus c. And there we go. So that's integration by parts twice. Now here's really why we do it. Notice in u it was t squared. The first part was t squared and the derivative is 2t. So we still have a t left. But once I differentiate t, now I'm down to having no variables, and that's helpful in du. If you don't have any more variables left, you just have the dt, usually that's something then you can integrate. So sometimes it kind of depends on the power of this first variable, like t squared. How you're going to have to do it is a couple times to get rid of that until eventually you get the derivative is 1. So that's why sometimes that can indicate that there. You can leave this as the final answer. You could distribute the 2 in, the 2 over b if you wanted to. Either of those forms would be fine. So it's a matter of what you want to do there. You can't really combine any like terms, but you could distribute that in. If you don't, make sure that you leave it in brackets so we know what it applies to there. Okay, so integration by parts twice. That's some fun stuff, right? Yes, no, okay. You're not as enthusiastic as I am. I can't understand it. Okay, right. After you try it, yes. Right now it seems horrible, but maybe by Monday you'll love it. Okay, so let's look at another one here. This is the integral of the natural log of x squared dx. Okay, natural log of x squared dx. Definitely don't know how to do that integral just as it is. So, what are we going to let be u and dv? Yeah, the u has to be the natural log. Did we talk about that yesterday? Really, anytime you have a natural log, you don't really know how to integrate that. So let's make that the natural log of x squared, right? The squared's on it, so we've got to take it with it. So then what does dv have to be? Dx, right? So that's just the dx part. Okay, so now let's see if we can determine what du and v are. Okay, do you remember how to differentiate natural log of x when it's squared? What rule do we got to use? Chain rule, right? So chain rule is differentiate the outside, so power rule. So drop down the 2, right? Make it to the first power. And then you times by the derivative of the inside, which would be what here? 1 over x. Good. Chain rule. So derivative of the outside, drop down the power, subtract 1, then times by the derivative of the inside. What's the integral of dx? X. Good. Just an x. The integral of 1 is just x. Okay, so following our formula, now we got to fill in uv minus integral of v du and see what we get. So Benham, help me fill this in. So what's uv going to look like? Okay, good. Minus the integral of? Okay, 2 ln x. What happened to the other parts? Yeah, what happens when you take v times du? What cancels? The x's. So you could write that down and show they cancel, but you'll get rid of them. X times 1 over x will be gone, and you should just have 2 ln of x. Yeah, so he kind of simplified. He saw that x and 1 over x were going to cancel. Yeah, sure. For sure. Okay, do we know how to integrate the natural log of x, or 2 natural log of x? I don't have a formula, right? There's not a formula for natural log of x, so I'm going to have to see if I can integrate it again. So I'll pull the 2 out front, but how are we going to integrate the natural log of x dx? Well, I know there's no formula, and definitely substitution probably won't help, so I'm going to try integration by parts again. So that's what I'll look for here. So I'm going to set up another u and dv for ln of x and dx. Which one would have to be the ln of x? The u, right? So that's right. And I pulled my 2 out front, though you could put it in with it if you want. So that has to be the u, because I don't know how to integrate, and so this has to be dx again. Okay, so if that's the case, McKelty, what's the du going to be? What's the derivative of natural log? Yeah, so 1 over x dx, or dx over x, good. And Jessica, what's our v going to be? What's the integral of dx? Yeah, x again. Good, I like that. So now we're going to integration by parts formula on this one. So that will be the uv minus integral of v du. But I'm going to bring the rest along. X ln of x squared. I'm going to have a minus 2 in front of the whole thing. So I'm going to put in brackets what we're going to get for the integration by parts on the second one. Okay, hopefully we got it here. So let's fill that in. Taft, do you want to help us there? What's the uv going to be? from my second ones with the capitals. So we're following this formula, right? So what are we going to have here? It's going to be? Good. So x ln of x, good, minus the integral of, what's going to happen when we do v du? Yeah, because the x's cancel again. So x times 1 over x will just be a 1 dx. And that is very easy to integrate, so we should be able to finish this off. So good. So x times 1 over x, those cancel. So we'll have x ln of x squared minus 2 times x ln of x minus the integral of dx, which is just what? X. And then we'll put at the very end our plus c. Okay. So there's another case where we got to do it twice. And again, remember, you can, if you want, distribute, if you don't like brackets, 2x ln of x plus 2x, that's acceptable too. It's really how you want to write it, but those would be acceptable forms. So you'll notice again on this one it had a squared power, and so basically we had to do it twice until we ended up with no really that variable being gone there, so we could integrate. Yeah, Riley? Yep, exactly. So now we know. So notice what we got when we integrated ln of x. We got x ln of x minus x. So we do know how to integrate it now. You use integration by parts. You can get the answer to that. So, yeah. Interesting that we can now integrate the natural log of x. All right, let's do another one here. So all of those kind of had some powers on our functions, and then with another piece. This is a function that has an exponential with a trig function. So let's see kind of what happens in this case when these are kind of put together. Is it going to, do I have to do it twice? What's going to happen here? Am I going to be able to integrate this? So we'll start by just setting up basic parts and then see what happens here, and hopefully we'll have a technique for solving this. So u and dv, I don't know how you want to choose this one. There's e to the x and cosine. The nice thing is we know how to integrate and differentiate both of those, right? They're not that hard. Let's just pick one. What do we want to be u? Cosine? Okay. So let's do cosine x here, and then dv e to the x. Okay. All right. So du. Riley, what's going to be our du then, if that's cosine? Yep, negative sine of x with the dx. V, what will that be? Let's see, Jeff, what's our integral of e to the x? V gonna be. What's v going to be? So if this is e to the x, what would you get when you integrated it? Yes. Easy, right? That one's just e to the x. Yep. Okay, so following along in our formula, then we're going to fill in the uv minus the integral of v du. So let's fill that in. So I'm going to have uv, I'm going to put the e to the x in front. So it's going to be e to the x and a cosine of x. The order doesn't matter, but e to the x will be with cosine of x. And then I'm going to have the integral of v, which is e to the x, and du, which is negative sine of x, right? So I'm going to actually put the negative in front and make it a plus, sine of x dx. Okay, so uv minus the integral of v du. Okay, I think I got it right. Can I integrate e to the x sine of x? What would I use to integrate e to the x sine of x? Parts again? Probably. That's what it kind of looks like up here, except now it's sine. So I'm probably just going to have to set up some parts again. So let's do it again. And remember the last time we chose cosine, so maybe this time we'll choose sine, I guess, and e to the x, which shouldn't be too bad. What do we get there? So what's the du going to be here? Salvador, what's if this is sine of x, what's du? Cosine of x, very good. And Jonathan P. here on campus, what's the integral of e to the x dx? e to the x again. Right, okay. Okay, this is going to help us. Let's see. So we're going to do the uv minus integral of v du on this integral as well. I'm going to bring along the e to the x cosine of x plus, and I'll just put it in brackets to separate it. This one doesn't have anything to distribute out front, but just so you can see it here. So that's going to be uv is e to the x sine of x minus the integral of v, which is e to the x times du cosine of x, and that has a dx on it, right? Yeah, what happened? Angie saw it. What did we get? We're back where we started. It's like we went in a circle and ended up with the same integral. Isn't that what we're trying to solve? Now this seems bad, but it's actually good. Here's why. I'll show you. So remember, this is what the whole thing is equal to, right? I'm going to put that in the front. So that original integral is equal to this. So now what we can do is actually solve for this integral. Notice there's one over here. It's being subtracted. I could add it over to the other side. If I add this over, how many of these do I get? 2 of them. So I'm going to add this to the other side. So now what do I have left is e to the x cosine of x plus e to the x sine of x. So once you get back to the original one, it's actually a good thing because you can combine them on one side, and then all I need to do is get this by itself, and I'll have what it's equal to, what its result should be. How do I get this integral by itself? What's the only thing I need to get rid of? The 2. So I just go and divide both sides by 2, and there's my answer. Because notice on the right-hand side, there's no more integrals left. So I don't need to integrate anymore. On the right-hand side, it's already done. Once I moved that one over, there were no more integrals left. So you might write this like this, maybe a 1/2 out front, or however you want to write it is fine. You can leave it as a fraction. Some people will write it like a 1/2 out front. So this is 1/2 e to the x cosine of x plus e to the x sine of x. The only other thing I should probably put at the end is just the plus c. And then you're done. So this is an example of one that's kind of circular, like you integrate by parts and you end up with something you started with. That's not necessarily a bad thing, especially if it's being subtracted, then you can add it to the other side to match them up and then solve for your integral. Okay. This happens a lot when you have an exponential and a trig function together like this. I should also mention that on this one, it actually would not necessarily matter what you chose as your u and your dv. If we had switched these around, we'd actually get the same answer. Because they're both kind of, these have its own integral and these switch back and forth between cosine and sine. So in this particular one, it actually wouldn't matter if you had chosen those differently. Though I should mention, once you start choosing your u's to be the trig functions and the v to be e to the x, you shouldn't switch in the second time. So if you've already set these up here as u and dv, don't try to switch those the second time. That will kind of lead you down another path that will not get you to the answer. So, yeah, trig's a function with an exponential. They call those transcendental functions, those types that aren't polynomial. So anytime you have a transcendental times a transcendental, that tends to be the technique we use. Yeah. Yeah, don't switch the u's and dv's in the second time you do it. So stick with whatever you've chosen to begin with and kind of follow that pattern. Yep. Okay, let's do one more for this. Trig functions. This one has secant cubed of x dx. And how we might use integration by parts with this. What do you think about secant cubed of x? If we're trying parts, and we want to choose u and dv, like secant cubed, I don't know, I can't integrate that, right? So it can't be the dv. But if I choose this to be u, that's not a very nice du, is it? Yeah, that's kind of like, then you have to use a chain rule. You'd have to drop the 3 down. 3 secant squared times the derivative, which is secant tangent. Seems fairly complicated. So I'm going to show you one thing you can do with a trig function like this that has kind of a higher power. You can split it up. So secant cubed, you could possibly write it as a secant squared times a secant. Okay, so remember cubed, you could split up into 2 and 1. And then maybe choose the parts from there. Because what do we know about secant squared? I can't do much with secant cubed, but I do know something I could do with secant squared, right? What can I do? Yeah, it has an integral, right? Yeah, so this would be a good choice for dv because I can integrate that. And in fact, it becomes what? The tangent, right? Tangent? Is that right? Okay. The integral of the secant squared is the tangent. And then u could be the other piece, which is the secant of x. So you know the derivative of secant, right? What's the derivative of secant? Secant tangent. There you go. Okay, so let's go ahead and follow our rule here. So we've got uv minus the integral of v du. So filling that in, u times v, what are we going to get here? Nathan, you want to help me with that? What's our uv going to be? Good. And then what will the integral be? Mind the integral of what? That's right. So if you multiply these together, you get a tangent squared and then a secant of x dx. Okay, now notice that doesn't really match up to what I have at the beginning, so I didn't get that. But I still, as it is, this would not be easy to integrate, right? I don't think so. Even if, can we try, even a u sub wouldn't be easy, would it? Because we could let u be tangent, but its derivative is secant squared, and we don't have that here. We just have secant. If we let u be secant, its derivative is secant tangent, but we have tangent squared, so that's not going to work. Okay, so what do you want to split up the tangent into? Tangent, tangent? Okay. So you want to write it as 2 tangents, right? I'm assuming. Like that. And then do integration by parts. Okay, let's try it. So what would you make your u and your dv then? Right, because that has an integral, right? So that'd be secant tangent, because that has an integral, which is secant. So the integral of secant tangent is the secant, right? So there's your v. What's the derivative of tangent? Secant squared. Okay, so what are we going to get here? Let's see. Bring this along and put it in some brackets. So remember, you want uv minus the integral of v du. So uv is another tangent x secant x, isn't it? Am I right about that? Tangent secant minus, what's the integral going to have under it? Secant cubed x dx. Okay. Did we get back what we started with? Yes. But let's see what happens in this equation. So I'm going to put the first integral back in here, the integral of the secant cubed. What is technically the sign in front of the secant cubed over here? Plus. So what is going to happen? And what happens to these two? Yeah. So notice what happens here if I go ahead and distribute the negative, these two cancel, make 0. And if I subtract this over, those make 0. It's like 0 equals 0. So I solved for nothing. Unfortunately, I did not get the integral by itself, right? So in the last one, notice it had a minus in front, and then I could add them and combine them. But when I end up with a plus here, that's going to be a problem. So we have to go back and try something else, but not all the way back. So what happened here is we got those to cancel out, and that was an issue. So we're going to start from here and try a different integral for this, okay? So obviously this didn't work. I'm just going to cancel it out and start from here, okay? I'm not saying what you did was wrong. Sometimes we've got to try it and then see that that's not really going to help us get to what we want. What happened? Oh. It's coming? Okay. You're right. Something's going on. Okay. How about, do you know an identity for tangent squared of x? Let's see if there's another way we could do this. What's the tangent squared identity? Secant squared minus 1, right? 1 plus the tangent squared equals secant squared. So we could replace that with secant squared of x minus 1. So let's go ahead and try that and see if that helps me at all. So the parts didn't work. What about an identity? So if I distribute that through, let's see what we get. So I get the integral of, what am I going to get if I distribute this through? Secant to the what? Secant to the third x dx minus a secant of x dx, right? I'll have secant cubed minus secant. Is this better? Right. Notice we still got back what we started with, but what's in front of it is now a negative. This is much better. So I think now I will be able to solve this out. They won't cancel out, and I should be able to solve this, I hope, from here. If I add this to the other side, I can combine them, right? Now I do still have this integral left. Can I integrate secant? Yeah. Remember, we can integrate all trig functions now if they're to the first power anyway. So let's do it. So let's add this one over. So there's 2 of them. And we'll integrate the secant. Who has the formula for the integral of the secant? And in fact, actually, that should be a plus, shouldn't it? Did I forget there? This is minus is the whole thing, so that will be a plus. Natural log of the secant plus tangent, is that right? Okay. Secant x plus the tangent of x. Yep. So I'll tell you what I did right here. So this one I added over to make 2 of them, right? So I added this one. It was minus secant cubed, became 2 of them. And then I went ahead and integrated this. And I distribute the minus through so it became a plus. Yep. Yes, right here I just distributed those out. Yep, that's exactly right. Good. Okay, what's my last step here? How am I going to solve for the final answer? Divide by 2. That's it. And maybe put something at the very end. What are we going to attach to the end here? Yeah, the plus. So, plus C. Again, you can put it out as 1/2 out front or the whole thing over 2. Either one is fine. Okay, well, we better stop for today since the time is out. So we'll stop there for today. Most of the ones in your homework you'll be able to do integration by parts, but it may take a couple times, or like this, where you get back what you started with. So I'm going to hand around the attendance. We start here, Benham, and just sign there. I know some people put a check mark, but if you will just put your initials, that would be better than a check mark. So I check them off in the outreach centers, but it's good to have your initials on there. Yeah, so 7.1 part 2, that will be due on Monday. So work on that over the weekend.